Hello and welcome to Security Outgunned, Measuring Software-Defined Attack Surface. If you're joining us live, our speaker is in this Slido discussion now, answering your questions. He will also be participating in a live Ask the Expert roundtable on this topic right after this session. For audio or video issues, you can click the technical support button below. I'd now like to turn it over to Rich Seierson for the presentation.
Thank you. Thank you very much. And yes, I'm Richard Seierson. I'm a serial recovering CISO. I was a CISO for Lending Club, one of the larger fintech organizations in the US. Prior to that, I was the CISO and VP Trust at Twilio, which is a cloud-native, a publicly traded cloud-native company. And prior to that, I was CISO at GE Healthcare. Along the way, I got very interested in how can I optimize my fighting the bad guys, right? And what I realized along the way was the best thing I can do is make sure I'm getting the best technology. This is on top of already having great teams. And when it came to having the best technology, the question was, how do I optimize that? How do I go about making the best decisions? And what I realized was that it was really about return on investment. And what I mean by that is return on investment in terms of the spend, the dollars, really in relationship to the effectiveness of the products, right? And then it dawned on me, how can I do that as efficiently as possible? And what I mean by efficiently was, how can I learn and actually have two products compete one against another, and within maybe a month, maybe a week, or sometimes, and you'll see later, maybe even a day, come to a conclusion with a small amount of data and, honestly, a lot of uncertainty. And so that's what I'm going to walk you through today. How do you control, really, software-defined attack surface? And I'll talk more about that, with making the best technology decisions possible. So let's talk a little bit about software-defined attack surface before I get really into the slides. So my last two CISO jobs, I was actually working in cloud-native environments. So what is cloud-native? Cloud-native is what allows developers to release code really rapidly. So maybe you were doing 100 or 1,000 releases a year previously. Now you're able to do 10,000 or 100,000 or more. So the first cloud-native company I worked for was doing, actually over 5 years ago, 30,000 releases a year. They were a cloud-native company. And what I realized was that it was absolutely critical that I had the best investments in technology, particularly when it came to vulnerability management, specifically dealing with web application vulnerabilities and API vulnerabilities. So the use case I'm going to talk to you today through is how to go about measuring and making the best decisions when you're confronted with a similar sort of scenario, and how do you go about doing really quick data science to make the best decisions. Well, here we go. All right, have fun. First of all, this talk is going to be somewhat technical, and I went ahead and wrote a whole tutorial for you. So if you go to this blog post, you go to the soluble.ai site, hit blogs, you'll see the blog post for this. It's long, it's like over 3,000 words, so I don't warn you about that. But there's code inside. There's a link to a whole set of code there, and it's really easy. You don't need to know how to do software. You really don't need to know how to do math or data science. I make it really easy for you. So again, I'm going to give you the highlights, show you how to think about this, but you can go ahead and run this all yourself. So all right, this is where we start. There's going to be 3 steps. And the first one I'm calling believe, therefore I measure, right? And it's an approach to reducing attack surface by reducing errors. So what do I mean by believe, therefore I measure? Well, Daniel Kahneman. I don't know if you guys know who he is. He won the Nobel Prize in 2003. He's a decision psychologist. There's such a thing, decision psychologist. He's one of them. He won the Nobel Prize in 2003. As an economist, though. Actually, he's not an economist. He's a decision psychologist, but he won it for work as related to being an economist. And most of the work he does, in many ways, is around beliefs, around calibrating your beliefs, and being really better at making decisions while you're dealing with a lot of uncertainty. So that's what we're going to do here. Okay? So, first step. Listen, when you are a CISO, you are totally outgunned by engineering. The normal organization, you're talking typically 100 to 1. When you get into cloud-native scenarios, you're talking about much more than 100 to 1. And you're going to have a little time, and you're going to have a little budget, and a little bit of data, right? You're going to be working lean. And so the first steps is, how do I go about thinking about reducing my external-facing vulnerabilities? Again, you're dealing with 100, maybe 200, 500 to 1. You have developers who are producing possibly, like my example, tens of thousands of releases a year. So the thing is, how do you go about deciding on what's the best solution. Let's say you're given two opportunities. You're going to do a proof of concept, right? You're going to take a week or a month to test two products. You're going to point them at the same solution, and you're going to want to measure the errors, right? So how do we go about doing that? So first of all, we're going to start with measuring your beliefs. Now, this is going to sound odd. You may think that that's a strange thing, and if you feel that way, then you're probably normal, so don't worry. But again, we go back to Kahneman's work and others, and if you look at my first book, actually, we go about this in detail. How do you go about measuring your beliefs, and why would we want to do that? Well, first of all, you're probably clear that in terms of errors, that is, false positives and false negatives, you're probably pretty clear that your product or any product doesn't produce errors 100% of the time, all the time. If that was the case, nobody would be buying vulnerability management solutions. You're also probably experienced enough to know that 0 is also not a use case, right? You probably have enough experience to have a vague idea of the vulnerability rates, particularly if you've been doing this for a while. I've been doing it for well over 20 years, and I have a pretty good idea of what the vulnerability rates are. I don't have a perfect idea, but I have some ideas, all right? So we're going to quantify your beliefs, and we're going to require 2 probabilities from you, all right? Now I'm going to show you an example, so I'll use some technical terms here, but I'll walk you through it. The first one is your median error rate. The second one is your 90% boundary rate. Again, if you don't know what those mean, don't worry about it, all right? So let's assume we're talking to a well-informed practitioner. They're a security practitioner, and they actually know what these words mean. What might they say? They might say, well, our median error rate is 25%. And what I mean to say is that the true rate is just as likely to be below 25% or is above. So what they're kind of saying is it kind of teeters around this 25% mark, and it kind of moves around there. If you don't know exactly what it is, they're kind of ambivalent. It's either below or above, all right? Then the next question is in terms of their 90% boundary rate. And all they're trying to say here is that, you know what, I'm confident. I'm pretty confident it's at 45% or below. I mean, it could be a little bit over, I don't know. But you know what? I bet you most of the time it's below that number. That's all I know. I'm not sure, right? So after all, I have never in my life experienced a 50% error rate. By the way, I have never experienced in a real product that I've actually bought a 50% error rate. I've seen some error rates that are pretty close to that, but I've actually never experienced that myself. All right. So if you were to go to my blog and you were to download my code, which is all free, given to you, and by the way, excuse the errors if there are any, you have a very simple configuration that you just enter. You can enter 2 numbers, right? And don't worry if you don't know about the exact numbers. This is not about being exact. By the way, it's all written in R. That's why you see the R t-shirt there. Go R, all right? So if you do that and you end up running the code, you're going to get a graph that looks like this, right? And that graph represents both our uncertainty and our certainty. And we're actually pretty uncertain. And in fact, if that graph could speak, it would say something like this. Given your beliefs, you should expect that the true rate is likely somewhere between 6% and 56%. We're not saying that it's actually there. We're saying it's probably there. And if you were to be forced to make a bet today, you'd probably want to bet in somewhere in there. In fact, you'd probably want to be betting somewhere close to where the amount of data seems to be the densest, right? All right. So next, you've got your beliefs. Now we're going to collect real data, and we're going to munge the belief data that you just created with your actual empirical data coming from your tests. So let's walk through that, all right? So there's your beliefs, right? We're going to take that, and we're going to actually add it to some real data. So let me explain this here. Again, that's R. If you go into the code, you'll see that there. Now, the first number, that 100,000, that has to do with simulations. I'll talk about that in a moment, but we're going to run this thing 100,000 times. It's going to be awesome. You can do it 1,000,000 times, too. You can change this configuration. All right, so you're testing actually 2 products. You have them under proof of concept. And let's say you're just going to have them run in the background for a month against the same set of applications. In this case, one of the tools produces 30 critical vulnerabilities, the kinds that you would normally want to fix. It thinks there's 30 of them. The other tool happens to think there's 37, right? So again, at the end of the month, you collect that. Let's say you're looking for CVSS 10 or whatever it is you think is really important. Pick your poison. You're going to select that. One says 30, one says 37. You enter that here, right? What's going to happen when you do the simulations, though, is you're going to create really what's a virtual reality. You're going to create 100,000, actually 200,000, one for one product, one for the other. So you have 200,000 scenarios, okay? So what happens next? So you've run this thing a bunch of times. What is it doing behind the scenes if you pop the hood? It's going to add these things essentially together. So what does that look like? So first of all, your beliefs, it simulates 100,000 for product A and 100,000 for product B. When I say simulates, it's actually picking out random values from under that purple curve, right? And it's going to pick more frequently from where it's most densest. So there you go. It spits out a bunch of stuff. And then what's going to happen is you're going to say, all right, given my beliefs, given this purple curve, and given, let's say for product A, 30 events, what does our model think is potential probable error rates? And that's what you see here. There's a model that's going to generate 100,000 potential errors, right? And then it's going to do the same thing for product B, which actually has 37 events, 37 vulnerabilities. But how much of that is actually errors, meaning false positives and false negatives? Again, it's just simulating it. It's like really low touch, very naive data science. And again, the blog post goes into this in a lot of detail. All right? So what happens next? So next, we're actually going to go and collect our errors, right? So it's end of month or end of week, however long your test is, you're going to have errors. By the way, you're going to be still somewhat uncertain about your errors. You'll have false positives. And by the way, when you look at them, you'll probably be able to discover them. Or maybe development comes back and says, hey, this stuff's unreal. And you'll have false negatives. Now, false negatives oftentimes can be from competing one product from the other. And the code actually helps you figure that out. And sometimes you'll find out about false negatives later, right? We're highly uncertain. That's okay. We're Bayesians, which you'll learn more about in a moment. We're going to go ahead and feel free and easy with uncertainty. Again, we're not looking for perfect. We're looking for better. All right, so what happens now is you have all this data. Remember the 100,000? What you're going to do now is you're going to filter away everything that's not 10 for product A or 13 for product B, right? You're going to be left with several thousand result sets, right? And then what's going to happen with those results, actually, let me tell you what you just did here. This is actually called approximate Bayesian computation. That's a really fancy word for something that's really simple. Basically, all we did is we filtered away the result sets that didn't represent the actual error sets we got. So our belief is there's some random generative model or generative process that's operating in the background and it's producing these results. We're highly uncertain. We don't know, but we think there's some vague process. We're trying to model that process. We're trying to model the generative process that's running in the background. That's approximate Bayesian computation. Look it up. There's more information on the web than you could shake a stick at. All right, so what we end up doing then from the ABC process, we then take those results, we filter down, and we might have several hundred, several thousand that are left. We're then going to simulate. Simulation means we're just going to generate a bunch of extra data from the data that we have. And what we're going to do is actually get 10,000 results in each case, right? So it's going to end up being two chunks of data, really almost thinking of them as like two separate databases. And now we're going to ask some questions. Again, the question that we're trying to get at is, what is the underlying probable error rate for product A, product B? And you can see the results here. Listen, if you want just one number, apparently the model, which is filled with our assumptions, and filled with tiny uncertain data, the model seems to think that product A has a 33% error rate. Again, it's not the correct error rate, it's just what this model thinks, right? And product B seems to think there's a 34% error rate. There's some variance. You can see the variance. Actually, this is a credible interval. It's actually the highest density. It's HDI, highest density interval for you statisticians out there, you Bayesians. But this is what our model thinks. So let's take it a step further, all right? Let's look at some graphs. The graph of product A data that we just simulated is on top, and product B is on the bottom. They look almost identical. Product A looks like it creates a little bit less errors. Let's actually model these one on top of another. It's always fun to take graphs and play with them and look at them from different ways, right? That's different. We can see some information that looks, again, like product B may be creating more errors. We're highly uncertain. They're really overlapping. And here's another view. We're actually going to subtract the rates of error B from error A. And what we see is more negative data, right? If you look at the product diff events on the right-hand side, you look at the graph, you see there's a little more data shifting to the left. That just tells us that product B seems to be creating more errors. Again, it's simulated. We're highly uncertain. We're not sure. Okay? So now we're going to take that data and we're going to munge that data. Again, we had our beliefs. We took some small empirical data, and now we're going to munge that together actually with some financial data. Isn't this exciting? All right, here we go. So This is really me being lazy. By the way, I recommend you to be lazy when possible. Developers are very lazy. I got my start as a developer, and now I'm really a lazy data scientist, CISO, CEO, right? So what we see here is a model of what I think is the range of hours that it takes to address an error. So when it comes to a critical false positive, we don't know it's a false positive yet. We need to go through and do some analysis. We look at the results. A security person, I may need to go talk to a service owner, I may need to talk to a developer, and again, if this is a critical vulnerability, I imagine it's going to take some time. I'm kind of thinking it's roughly around 2 hours. It could be as low as 1 hour, it could be as much as 5, right? So, but it's kind of fluctuating and, you know, moving around in that space vaguely. And the same with cost. I've modeled cost here for California in the Bay Area. I'm saying, yeah, you know, I believe it's going to be 2 people participating. It's going to be kind of somewhere around $600. This is fully loaded, right? Like in terms of salaries, right? With taking into consideration benefits and real estate and whatnot. And I think it could be as low as 200 and as high as 2,000, give or take, right? So again, I have some fluctuating vague idea of the hours per incident, be it false positive or false negative, and I have some idea of the costs. All right, so what are we going to do? Actually multiply this all together. So again, we have those rates on the left-hand side here, the rates for product A, product B. Again, those are there's some variation or distribution of error rates that we simulated. We're then going to multiply that together with the hours and with the costs, and we come up with some impacts. And these are the expected value of the impacts, right? It's not the actual impacts, right? This is only a model. I mean, think about this. If you have your phone, you have a map up, and it's, you know, it's a map from your home to the restaurant you want to go to, and you were to go outside and compare that map to the actual concrete, you'd be pretty dissatisfied if your expectation is that map's supposed to look like the concrete. That's not your goal. Your goal is actually to make sure you go from point A to point B, and that's what we're trying to do here. We're trying to be a little more informed about how we get from point A to point B. So we have product A impacts and product B impacts. The reality is we have a whole distribution mountain of data for each of these, and we can go ahead and do all kinds of interesting analytics if we want. I'm making it easy for you. I've picked a number that's called the expected value. It's a way to be mathematically unambiguous and consistent when we go about comparing things. But again, we're not taking a map and saying that's the road exactly. So let's go ahead and take those expected values and compare them to one another. And guess what? Hey, they look almost identical. They're not exactly identical, but from a visual perspective, they look pretty darn close. So let's go ahead and see what our month 1 scenario, again, we let these two things just go at it in the background. Or we can actually run this automatically. The R can be hooked up to your Jira system or ServiceNow. It can just run and give you these results. It can give you results, by the way, on a daily basis. You can do blow by blow if you want, minute by minute. You know, dealer's choice. But for product A, it looks like there's a 90.8% chance that the total cost, that A is the total cost of product B. It means A in terms of cost and errors is going to be a little less than product B, right? It's not a lot, by the way, right? It's 148, call it 149 versus 164,000, right? For most large companies, that's a rounding error. I don't consider that to be a real big deal. And by the way, it's not reality. It's only a model. But if we had to make a decision, if you were forced to make a decision with all this uncertainty, with a little bit of time, a little data, you might make a bet this way. But hey, let's say that you are a company that's doing cloud-native development, and you are producing lots of vulnerabilities in a week. You could run this model. You'd say it's the same data set, but instead of a data set that came over a month, it's a data set that came actually over 1 week or 7 days. In this case, we're starting to see a little more information. What we've done is we've actually created more data in a shorter period of time. By the way, when you have a lot of uncertainty, how do you solve that problem typically? More data. That's kind of what we've done here. So now we have an 81% chance that A is the total cost of B, meaning A is cheaper. So we're looking at $372,000 versus $459,000. That's not real, by the way, right? I don't expect that you're going to write a check. By the way, this is forecasted over a year. I should have mentioned that. Sorry, I didn't. But this is forecasted over a year. I'm not saying that you're going to experience this as some sort of tax where you write a check. You're looking to optimize. This is a way for you really to understand how much you're going to impact your developers, by the way. It's a way for you to say, okay, if I'm looking to optimize, I'm looking to produce less errors and have overall less financial impact. I'm really looking to create less drag from my team, my developers. I'm going to say, hey, look, if this is your data, clearly you should go for product A. By the way, we're highly uncertain. It's not the truth, but given only this information, your beliefs, I'd go with this, right? That being said, if you have a really shiny product and it costs more, but you're super excited about it because you like to buy shiny things, and the shiny thing happens to be, $460,000, then go for that. So let's say you work for one of those cloud-native companies like I did, where they're doing 30,000 releases a year, or you work for Airbnb, or you work for Facebook or Netflix. Well, you might be able to generate the same sort of data in one day. I don't think anyone would ever do a proof of concept in one day. I think you'd probably want to do it for at least a week or a month. But if you did that, our model would say, hey, look, based on this error size, you're looking at this differential in terms of impact. It's not real. It's only a model. It's a mathematically unambiguous and consistent way of comparing things, right? I'm not asking you to believe in it, but I'm asking you to consider what the alternative is. The alternative, if the alternative to something like this is your gut, your subject matter expert opinion, which is really your gut, what's going to happen is typically you're going to end up probably choosing the shiny thing. That might be fine. That might be your model. If you're looking for a bit more, you can use this. So what have we learned? We've learned that you can measure your beliefs. You can naively measure your beliefs. I'm going to say that you know something about security. You're a security expert. I'm going to believe that you actually know something about vulnerability error rates. If you think that anything is always possible all the time, meaning it's just likely to be 100% to 0%, I'm going to say that's a reflection of you not actually having any experience. That's fine. You shouldn't be doing this, right? Second step is measuring actual errors and then munging those together with beliefs. And we did that using a simple Bayesian model. The third step is measuring costs. I used a hyper naive model for measuring costs. We can go into a lot of complexity for doing that. We chose not to do that here. We use some real simple inputs, right? And then my view or my belief is lacking anything else, you can use the results to inform your beliefs. You can use this model for any sort of security product you like. I chose vulnerability management. I chose to deal with externally facing APIs and web application vulnerabilities because that's something that I deal with a lot and I have my whole career. But any sort of products you're looking to proof of concept are going to have errors. They're going to make mistakes. Again, you're looking for the things that go right, all the stuff that actually works, that's the cost of doing business. You're concerned with the things that go wrong, the things they miss, which creates risk, which creates breach, or the false positives, which create extra work. Those are the things you want to measure, and you can measure those at ease using a model like this. That's all I have. I know I talk fast, but you have a 3,200-word blog waiting for you with about 800 lines of code waiting for you as well. So between this video, between the blog, and between the free code and all that, you should be good to go. Really appreciate your time. Thank you very much.